In our first lesson on simple filters, we found that almost all filters can be classified as low pass, to pass a range of frequencies up to a certain value and reject those above that value; high pass, to pass a range of frequencies above a certain value and reject those below that value; band pass, to pass a selected band of frequencies while rejecting all others; and band reject, to reject a selected band of frequencies while passing all others. We also found that almost all filters are simple combinations of inductors, capacitors, and resistors. It was the reaction of a particular combination of these components to frequency that produced filtering action. For example, this low-pass L-section filter has an inductor in the series position, a capacitor in the shunt position. The inductor offers a small impedance to low frequencies, a large impedance to high frequencies, thus will pass lows, reject highs. The capacitor works just the opposite. It offers a large impedance to low frequencies and thus develops a large voltage across it. Since that output is taken across the capacitor, the output voltage is large at low frequencies. At high frequencies, its impedance is small and it does not develop a suitable output voltage. No output at high frequencies. We found that we could reverse the action of the filter by reversing the filter components. The capacitor in the series position offers a large impedance to low frequencies and blocks them, and a small impedance to high frequencies and passes them. The inductor in the shunt position offers a small impedance to low frequencies and does not develop a suitable output voltage, while at high frequencies its impedance is large and thus it will develop an output. A series tank circuit placed in the series position of the filter will pass a band of frequencies around resonance and reject those above and below resonance, because a series tank offers minimum impedance to frequencies close to resonance and will pass them, but to all other frequencies it offers maximum impedance and thus rejects them. Placing the tank in the shunt position reverses the filtering action. The tank offers minimum opposition to frequencies around resonance, thus does not develop a suitable output voltage. The band of frequencies right around resonance is rejected. At all other frequencies, though, tank impedance is maximum. Thus, output voltage is developed. All frequencies off resonance are passed. That pretty well sums up what we covered in the first lesson on filters. Now, in this lesson, we'll see how a parallel tank circuit can be used in filter circuits. We'll also discuss several other filter configurations. But in each case, we'll find that all the principles we developed in the first lesson still apply to these more complex filters. So let's first determine how a parallel tank circuit can be used to provide filtering action. Remember, there are two basic positions for component placement in a filter circuit: the series position and the shunt position. Now we'll start by placing the parallel tank in the shunt position. Okay, we'll remove the series tank and replace that with the parallel tank. Okay. Now, since we only want to determine its effect on the input frequency, we'll use a resistor in the series position of the filter, because the resistor is not a frequency-sensitive component and it'll have no effect on the input frequency. Thus, any frequency effects we see in the output must be due to the action of the parallel tank circuit. Now, let's hook this up on our trainer and see what occurs. Now remember, we'll be using an oscilloscope, a little breadboard trainer, and a signal generator for our demonstrations, as we did in the earlier lesson. Remember that the input frequency taken from this signal generator is applied directly through these connectors up to this point on our little trainer. Now, through this direct connection, we can see the input frequency displayed on the A trace or the top trace of the oscilloscope. Now, this is the frequency directly from the trainer or from the signal generator, the top trace of the scope. The other lead here, the one in the middle, is used to provide a synchronization voltage or an external trigger for the sweep circuits of the oscilloscope. Now, down here, in this circuit here, is where we'll hook up our filter components. This is the series position, and here is the shunt position. Now, notice, as is always the case, the output is taken across the shunt component and is displayed on the B trace or the lower trace of the oscilloscope. Note also that, as we did in the first lesson, everything is grounded together. All right, let's plug in the components now. First, I'll put in the inductor. Remember now, we're going to make a parallel tank circuit. So we'll put the inductor in here, just like that. Now, there's the inductor. In parallel with that, we'll hook the capacitor, just like that. Now, there's our parallel tank circuit. Now, we need a resistor to complete the circuit, and we'll use one of the resistors that we used in the first lesson, variable resistor, set to the correct resistance to operate the circuit. Let me just get it plugged in there now. Okay. Now you can see that we do have an output from our circuit. There we're going through the resistor and the tank circuit to ground. Okay, now watch the output or the signal on the lower trace as I vary the input frequency. Now you see what's happening? The parallel tank in the shunt position is causing this circuit to function as a band pass filter. These frequencies below resonance are being rejected. There's not enough output there to operate the load device. But frequencies right around resonance are being passed. We have about the same output as we have on the input. So these frequencies are being passed. Now, these frequencies above resonance, however, are also being rejected. So we have a band pass filter. Now, as is true of all other filters, reversing the position of the shunt and series components reverses the action of the filter. Let's see. Now, the parallel tank is in the series position. The capacitor here, and across it, or in parallel with it, the inductor. Tank in the series position. In the shunt position, you'll notice that we have our resistor. Now let's check the frequency response of this circuit. At low frequencies, I have maximum output from the filter. But right around resonance, the output drops off to practically nothing. We're rejecting these frequencies right around resonance. Frequencies above resonance are being passed. So the parallel tank in the series position causes the circuit to function as a band reject filter. It's rejecting a band of frequencies right around resonance, but passing all others. Actually, the parallel tank works just opposite to the series tank. Now, both these circuits function as band pass filters. A series tank circuit in the series position or a parallel tank circuit in the shunt position serves to pass a band of frequencies around resonance, reject all others. So, why can't we combine the filtering components of the two circuits and make one band pass filter that has a series tank circuit in the series position, a parallel tank circuit in the shunt position? This circuit will still function as a band pass circuit, plus the filtering action will be improved because now there are two tanks to provide filtering action. To frequencies around resonance, the series tank offers minimum impedance, thus will allow them to pass through. The parallel tank offers maximum impedance to these frequencies, thus will develop maximum output voltage. And since the output is taken across the tank, the output voltage will be maximum at these frequencies. So the circuit has passed a band of frequencies around resonance. To frequencies above and below resonance, the series tank offers maximum impedance, thus will block or reject those frequencies. The parallel tank impedance is minimum to frequencies off resonance, and no output voltage will be developed. The circuit is rejecting frequencies off resonance. Now here's the series tank in the series position. Inductor, capacitor in series. And the parallel tank in the shunt position. It's our parallel tank inductor, our parallel tank capacitor. Let's see how this combination affects our output signal. As you can see, the circuit is functioning as a band-pass filter. Now notice the good attenuation of those frequencies off resonance and the sharp response of the filter at resonance. Now this is due to having two tanks providing the filtering action. As demonstrated in all other filters, reversing the series and shunt components reverses the filtering action. Watch. Now these components, the inductor and this capacitor, are hooked up as a parallel tank, and they're in the series position, and this inductor and this capacitor is hooked up as a series tank, and it's in the shunt position. Now the parallel tank is offering maximum impedance to frequencies close to resonance and rejecting them, and the series tank is offering minimum impedance to frequencies at resonance and is not developing an output voltage. The filter is now rejecting frequencies at and around resonance. At frequencies off resonance, the parallel tank impedance is minimum and passes these frequencies through. The series tank impedance is maximum and develops the output voltage. The circuit is passing frequencies off resonance. And note the extremely sharp response, since we're now using two tank circuits. We've now demonstrated all of the so-called simple filters. Next, we'll discuss modifications that can be made to the basic L section that will improve the overall filtering action by adding additional filter components to the circuit. We'll start out with the basic L section low-pass filter. The inductor in the series position of this filter will pass low frequencies but reject high frequencies. The specific frequency range the filter will affect will depend, of course, on the size of the components. If the inductor is 10 henries and the capacitor is 0.01 microfarads and the output is hooked up to the scope, as in our demonstrations, the frequencies passed will be below 600 hertz. Those above that value will be rejected. Now, changing the value of any of the components in the circuit will cause the filter to affect a different range of frequencies. However, there are a number of modifications we can make to this circuit without changing total inductance or total capacitance. And if we don't change the total values of L and C, then the filter will still affect the same frequency range. For example, if we split this inductor into two equal parts and connect the parts together like this, have we changed total inductance? Now, each inductor equals 5 henries. And since inductors in series are added just like resistors in series, the total value of inductance is 5 plus 5, or a total of 10 henries inductance. We can even move one of the inductors over here on the output side of the filter, and we still won't change total inductance. It's still 10 henries, and thus this filter will still pass frequencies below 600 hertz, reject those above that value. This filter is an inductive input-output filter. This particular configuration is called the T section because it's shaped like the letter T. This filter has several advantages over the simple L section filter. One, it provides better overall filtering because there's a filter component in both series legs of the filter, both the input and the output. Another advantage is that with this configuration, it doesn't matter which side of the filter is hooked up to the input. The impedance is the same in either direction. And this is an important consideration in circuit design. After all, this filter must be connected between two other circuits, and impedance matching between those two circuits is an important consideration. What it all boils down to is simply this: the filter configuration will be selected that best meets the requirements of the equipment in which it's to be used. In some cases, the simple L section will suffice. Other circuits may require a capacitive input-output filter. That, too, can be constructed from the basic L section filter following the rule we established earlier. That is, once the total capacitance has been determined that will affect the particular frequency range we wish to filter, we cannot deviate from that total value of capacitance. Well, since capacitors in parallel are added like resistors in series, we can replace this 0.01 microfarad capacitor with two 0.005 microfarad capacitors in parallel. The total capacitance is still equal to 0.01 microfarads, so the circuit will still affect the same frequency range. We can even move one of the capacitors to the input side of the filter without changing total circuit capacitance. It's still 0.01 microfarads. This configuration is called the pi section filter because it's shaped like the Greek letter pi. It has the same advantages of the T section, that is, better filtering and impedance matching between input and output. However, this offers capacitive input, where the T offered inductive input. Again, the choice of filter is based on circuit requirements. This same logic can be applied to all the basic L section filters. For example, let's consider the L section high-pass filter. To construct a T section filter with the same frequency response as this basic L section, we must use two capacitors in series. Since capacitors in series are added like resistors in parallel, each capacitor must equal twice the value of this single capacitor. So, 2 times C here on the input and 2 times C here on the output. Total capacitance is still the same as in our original configuration. This pi section version of the high-pass filter shows that we have two inductors, two parallel inductors. Since inductors in parallel are added like resistors in parallel, we must have twice the original value of inductance in each of our legs of the filter. The advantages of the T and pi section version of the low-pass filter apply equally to the high-pass versions and also to the band-pass and band-reject filters as well. Let's first consider how we can improve the filtering action in our band-pass filters. This L section band-pass filter can be configured as a T section following the rules established earlier concerning total circuit inductance and capacitance. We'll need another inductor in series, and inductors in series add just like resistors in series. So 1/2 the total inductance must go in the input tank, 1/2 in the output tank. Capacitors in series are added like resistors in parallel. So to maintain the total required value of capacitance, we must put twice the capacitance in this tank and twice C in this tank. Thus, total values of L and C remain the same as originally required, and this circuit, the T section band-pass filter, will still affect the same frequency range as did the basic L section. Note again that the input and output impedances are equal, and since we have more filter components, our filtering action is improved over the basic L section. The pi section band-pass filter can be constructed by, again, maintaining total circuit inductance and capacitance values the same as in this basic L section. We'll add an additional shunt leg to the basic L section like this. We now have two capacitors in parallel, so each capacitor must equal half the original capacitance. 1/2 here and 1/2 here. Two inductors in parallel, however, means that each inductor must equal twice the total value required. So 2 times L goes here in this tank, and 2 times L goes here. Again, total values of L and C have been maintained. And finally, we come to the band reject filter. It can also be reconfigured into a T or pi section. The basic L section band reject filter uses a parallel tank in the series position. To form a T section band reject filter will require 2 parallel tanks in the series position. Notice how total circuit inductance and capacitance are maintained by placing half the series inductance in each tank and twice the series capacitance in each tank. The pi section band reject filter has 2 shunt legs. Each leg has a series tank with twice the total shunt inductance in each tank and half the total shunt capacitance in each tank. Again, this is done to maintain total shunt inductance and capacitance at the required values. Now we have our demo hooked up as a simple L section band reject filter, a parallel tank in the series position, our little shorting wire, and a series tank in the shunt position composed of this capacitor in series with this inductor, and of course the other side of the inductor going to ground, and our output is taken across our shunt component. Now we've said that the T and pi section filters provide improved filtering action over the simple L section. What do we mean by improved filtering action? Just this. This L section band reject filter rejects a band of frequencies from about 500 hertz up to about 700 hertz. Now since the specific frequency we want to reject is 600 hertz, this circuit is not too precise, is it? So let's make a T section from this basic L section and see if we can improve the frequency response. Now to make the T section, we'll need another parallel tank in the output leg of the series position, and we'll need to move our series tank over to the junction between the 2 parallel tanks. Now let's do this. Okay, parallel tank here in the input series leg of the filter and a parallel tank in the output series leg of the filter. And our series tank now is connected from the junction of these 2 tanks down through the capacitor, the inductor in series, and down to ground. So we have a T section band reject filter. Now let's check the frequency response of this circuit and see if we have indeed improved it. All right. Notice now that I only have to go down to about 550 hertz and I have maximum output from the filter. The same is true on the other side of the frequency we wish to reject. At about 650 hertz, I now have maximum output from the filter. So I'm now rejecting a band of frequencies much closer to 600 hertz. I have indeed improved the frequency response of the filter. This is true of all the more complex filters. The additional filter components serve to improve the frequency response of the filter, to cause it to do more precisely what we want it to do. Well, that's it. You've now seen all the basic filter configurations and how they can be modified with additional components to form T-section and pi-section filters. Your classroom instructor will show you a page in your study guide which shows all of these filter configurations. As you study them, keep in mind the basic principles we've established concerning filter circuits and how they work. Later on, when you study receivers, transmitters, antenna systems, and other advanced circuits, you'll see these filters again. What you learn now will prepare you for those later studies. In our first lesson on simple filters, we found that almost all filters can be classified as low pass, to pass a range of frequencies up to a certain value and reject those above that value; high pass, to pass a range of frequencies above a certain value and reject those below that value; band pass, to pass a selected band of frequencies while rejecting all others; and band reject, to reject a selected band of frequencies while passing all others. We also found that almost all filters are simple combinations of inductors, capacitors, and resistors. It was the reaction of a particular combination of these components to frequency that produced filtering action. For example, this low-pass L-section filter has an inductor in the series position, a capacitor in the shunt position. The inductor offers a small impedance. Shunt position offers a small impedance to low frequencies and does not develop a suitable output voltage, while at high frequencies its impedance is large and thus it will develop an output. A series tank circuit placed in the series position of the filter will pass a band of frequencies around resonance and reject those above and below resonance, because a series tank offers minimum impedance to frequencies close to resonance and will pass them, but to all other frequencies it offers maximum impedance and thus rejects them. Placing the tank in the shunt position reverses the filtering action. The tank offers minimum opposition to frequencies around resonance, thus does not develop a suitable output voltage. The band of frequencies right around resonance is rejected. At all other frequencies, though, tank impedance is maximum. Thus, output voltage is developed. All frequencies off resonance are passed. That pretty well sums up what we covered in the first lesson on filters. Now, in this lesson, we'll see how a parallel tank circuit can be used in filter circuits. We'll also discuss several other filter configurations. But in each case, we'll find that all the principles we developed in the first lesson still apply to these more complex filters. So let's first determine how a parallel tank circuit to low frequencies, a large impedance to high frequencies, thus will pass lows, reject highs. The capacitor works just the opposite. It offers a large impedance to low frequencies and thus develops a large voltage across it. Since that output is taken across the capacitor, the output voltage is large at low frequencies. At high frequencies, its impedance is small and it does not develop a suitable output voltage. No output at high frequencies. We found that we could reverse the action of the filter by reversing the filter components. The capacitor in the series position offers a large impedance to low frequencies and blocks them, and a small impedance to high frequencies and passes them. The inductor in the